All right, hello there. So today we are going to learn about matrix inverses, how to determine if matrices are inverses of each other, what it means for them to be inverses of each other. We're going to learn how to find the inverse of a matrix, and then we're going to learn how to use the inverse of a matrix to solve the system of equations. Okay, so that's the objective of this video. This is from chapter 2, and it's kind of the end of chapter 2, which is our matrix chapter. So I'm going to start on this page that says matrix inverses, and I'm really not going to go into the additive inverse information at the top of this page. I'm going to talk more about multiplicative matrices because that's really what this is all about. So that word inverse, well, I meant to say multiplicative inverses is what we're going to talk about. So that word inverse means you put two things together and the result of combining them, we can combine them by addition, subtraction, multiplication, or division. If two things are inverses, then when you combine them, the answer, the result, will be what we call the identity. Now we're going to focus on multiplication today, and with multiplication, the number that is the identity is 1. The reason that 1 is considered to be the identity is because if you multiply any number by 1, that number stays the same. Negative 3x times 1 is negative 3x. So 1 is the identity. Now in matrices, obviously we can't have just a single number as the identity. So in matrices, we have a matrix that is the identity matrix. And the identity matrix, which we call uppercase I, that stands for identity, is this matrix that has 1s down the main diagonal and 0s everywhere else. Now, if our matrix is just 2 by 2, then it's just these two 1s here and the 0s on the other diagonal. When the matrices get bigger, we'll see what that identity looks like in a minute. We're only going to concern ourselves with 2 by 2 and 3 by 3 matrices. So I'm not going to go through the whole multiplication process here. I'm just going to suffice it to say that if you multiply this matrix by this identity matrix, it's not going to change anything. Okay, I could go through and multiply the rows and the columns, but I'm not going to do that. I'm just going to say, since this matrix is the identity, then when you multiply any matrix by it, that matrix is going to stay the same. So what we've learned there is that this matrix is called the identity matrix. Now, what are multiplicative inverses then? Well, like I said before, two things are inverses of each other if you combine them, and in this case, by combine, I mean multiply. Two things are inverses of each other if, when you multiply them, the answer is the identity. So we can think about, and the identity, if you're just multiplying, is 1, right? So if I multiply 144 by its reciprocal, if I multiply those, my answer is the identity, which is 1. So 144 and 1 over 144 are inverses. They are multiplicative inverses. What if we started with negative 3x? Well, its multiplicative inverse would be its reciprocal, negative 1 over 3x. So these would be inverses of each other because when you multiply them, the answer is the identity. With matrices, when we find the inverse of a matrix, we are finding what matrix would you multiply by this one in order for the answer to be that identity matrix. And so that's what we're going to be finding here. Okay, now there are instructions here. That's just some general facts. So to determine whether two matrices are inverses of each other, well, if you multiply them and you get the identity matrix, then the two matrices are inverses. I'm going to skip going through all of that because that's all you need to know. Now, there are directions down here at the bottom of this page for how to find the multiplicative inverse of a matrix. And you know what? This method works perfectly well, and it involves augmented matrices and row operations that we've learned how to do. But I'm going to show you an easier way, or a shorter way anyways, to find the multiplicative inverse of a matrix. Okay, so on the next page here, we're going to find the multiplicative inverse of these matrices. And right now we're only worried about 2 by 2 matrices. So here's step one. Step one is find the determinant. Now we remember how to find the determinant of a 2 by 2 matrix, hopefully. This is where we multiply the numbers on the first diagonal. So that would be 1 times 0. And then we multiply the numbers on the second diagonal, which would be 2 times -1. And we subtract those two numbers. So 1 times 0 is 0. And then I'm going to subtract. So I could think of it as -2 times -1 would be +2. And so my determinant is 2. And we're going to need that determinant in step 3. The second step here is what I call the swap and change. Now I know that swap and change seem like they're really the same thing, but in this case they're not. So what we're going to do here is we're going to take the numbers in the first diagonal and we're going to swap them. So instead of 1, 0, that diagonal will go 0, 1. So you see how I've swapped those two numbers. Now in this case, the word change is going to be what we do with the second diagonal, but change is going to mean that we're going to change the signs on these numbers. So that -1 will become a +1, and the 2 will become a -2. So we're not going to swap the numbers on the second diagonal. We're just going to change their signs. That's why I used two different words here. Step 3 in this process is going to be to divide every number in that matrix by the determinant. Okay, so I'm going to take all of the numbers in this matrix after I've done the swap and change, and I'm going to divide all of them by the determinant. Now, dividing by the determinant, well, the determinant is 2. So dividing by 2 would be the same as multiplying by 1/2. So in this step, I like to always just put 1 over my determinant, and that's my dividing by the determinant step. So now instead of dividing by 2, I'm multiplying by 1/2. But if you want to think of it as dividing by 2, that's perfectly fine. So I'm going through each of these numbers and multiplying them by 1/2 or dividing them by 2. So 1/2 times 0 is 0. 1/2 times 1 is 1/2. 1/2 times -2 is -1. And 1/2 times 1 is 1/2. And that is my inverse matrix. Okay, so this matrix here is my inverse matrix. That's what it looks like. I'm not going to go through and kind of prove that it's the inverse, but if I were to do that, I could take the original matrix and multiply it by this one, do row 1 times column 1, row 1 times column 2, row 2 times column 1, and row 2 times column 2, and I should find that when I multiply them together, the answer or the product is that identity matrix. Okay, let's go on. Now that we've kind of gone through the process, we can do this a little bit more quickly now. Okay, so the first thing is to find the determinant. So I'm going to multiply the first diagonal. 3 times 2 is 6, and then I'm going to subtract. And now I'm going to multiply the second diagonal. -5 times -1 is 5. So my determinant is 6 minus 5, which is 1. Ooh, this is going to be an easy one. Okay, so I'm going to do my swap and change. So the first diagonal, we swap those numbers. So 3, 2 becomes 2, 3. Second diagonal, we change the sign. So that'll become a +1 and a +5. And then we divide by the determinant. Now my determinant here is 1. If I divide all these numbers by 1, I'm going to get the exact same thing. So that's my inverse. I don't really need to do that dividing by the determinant step because I'm going to get the same answer, right? Okay, let's look at example C here. So step 1 in finding the inverse is to find the determinant. So I'll go ahead and do that. Multiply the first diagonal, which is 1 times 6, so that's 6. And then I'm going to subtract. The second diagonal is -2 times -3, which is +6. You'll notice here that I get a determinant of 0. Now this is kind of interesting because if I go ahead and do my swap and change step, And then if I multiply every number by 1 over the determinant, or divide every number by the determinant, I'm going to be dividing each of these numbers by 0. And we know you can't divide by 0. That's not an operation that's determined. That simply means that this matrix has no inverse. If the determinant is 0, your matrix will not have an inverse. When a matrix does not have an inverse, we have a special name for it, and we call that matrix a singular matrix. It's called a singular matrix because it's singular. It doesn't have a buddy. It doesn't have a matrix. We're going to get a little bit more practice with finding inverse matrices a little bit later, because I know we didn't get to practice that a whole lot. When it comes to 3 by 3 matrices, we are only going to be responsible for finding those inverses on our graphing calculators. Now, if you have a TI Inspire at home, that's great. I have a feeling that most of you don't. I'm going to go through the process for doing this on the calculator so that when you get back to school, you'll know how to do it. In the meantime, while you're at home, you know, I just did a quick Google search. For matrix calculators, and it's really easy to find technology tools on the internet that will do these calculations for you. Okay, so you can just Google like matrix inverse calculator, and you'll find some things where you just plug in the numbers and it'll find that inverse matrix for you. I'm going to go ahead and go through how to do it on the calculator though real quick so that you'll know how to do it when you get home. Or if you do have a graphing calculator with you, you can go ahead and use that. So I'm going to choose to open a new document. I'm going to say, no, I don't want to save whatever the heck that was. No, I don't want to save you. No, I don't want to save you. Okay, there we go. I'm going to add a calculator page, and here we go. So first thing I need to do is just enter that matrix. And the way that we do that is we go to this button that's just to the right of the 9. We hit that button. There's actually a few different matrix options here, but I'm going to choose this one that looks like a 3 by 3 matrix. And it says number of rows and number of columns are both 3, so that's what I want. So I'm going to hit tab twice and then hit OK. And then I'm just going to type in the numbers, so -1, and then I'm hitting the tab button in between each of the numbers that I type in. 4, 5, 0, 0, 1, -3, and I'm going to right arrow so that now my cursor is outside of the matrix. Now our notation for an inverse is to use an exponent of -1. So that's what I'm going to have my calculator do now, is I'm going to go to the exponent button, which is this little caret button that's right next to the x squared. I'm going to type that. You'll see my cursor goes up into the exponent, and I'm just going to type in a -1. So I'm going to type in a -1 and hit enter. And there it is. It gives me my inverse. I'm not going to take the time to copy all that down on the page, but that's your inverse matrix, and that's all you have to do. So I'll go through and do example E here real quick. So again, we go to the button right next to the 9. We choose the 3 by 3 matrix. We make sure the number of rows and the number of columns are correct. Hit tab a couple times and hit OK. Just type in the numbers, hitting tab in between each of the numbers. Hit right arrow so that your cursor is outside the matrix now. Hit that caret button, the matrix button, and just type in a -1 and hit enter. It says, uh-oh, you have a singular matrix. So we know what that means now, right? We know that this is a matrix whose determinant is 0, and therefore this matrix has no inverse. So we would just say there's no inverse here. This matrix is singular. I'll just say okay. All right, so we're going to go on to the next page, which is where we learn to start using matrix inverses to solve a system of equations. Okay, so here we have a system of equations. There's 2 equations and 2 variables. And in the past, we solved this by setting up an augmented matrix. And so for this problem, we would copy down the 2 and the 5 and the 15 and the 1 and the 4 and the 9. We put our vertical line to make it an augmented matrix. And then we just used our row operations until the left side of that augmented matrix was the identity matrix. And then whatever numbers we ended up with over here, those were our solutions. So this was an augmented matrix. And We called this the Gauss-Jordan method. Well, we're going to learn a different method now that involves inverse matrices. So what I'm going to do first here is I'm going to write an equation that involves matrices, and this equation is going to represent this system. So we call this a matrix equation. So we're going to write a matrix equation to represent this system, and it's real simple. The first matrix in my matrix equation is simply going to consist of the coefficients of x and y. So in the first equation, that's 2 and 5. In the second equation, that's 1 and 4. I'm going to multiply that coefficient equation by a variable matrix, which is a column matrix that just consists of my variables. So you can see if I were to multiply these, I'd have 2x plus 5y and 1x plus 4y. Okay, so that's going to equal a third matrix, which is going to consist of just the constant numbers on the right side of our system. And so this is our matrix equation. So you can see that that's different from the augmented matrix that we used last time. Here's a matrix equation. Now, how are we going to solve this matrix equation? Well, let me run you through that. It's actually not too bad. This first matrix, I'm going to call this matrix A. The second matrix is matrix X, and the third matrix is matrix B. So what we're really doing here is we're multiplying matrix A by matrix X, and that is equal to matrix B. We need to solve this for X. Well, you might think that we're going to divide both sides by matrix A, but we actually are not able to divide by a matrix. It's just not something that makes sense. We don't do matrix division. So instead of dividing both sides by matrix A, I'm going to multiply both sides by the inverse of matrix A. And so this is how we're going to solve for matrix X. We're going to multiply the inverse of A by B. We're going to do A inverse times B. So we need to find the inverse of matrix A. Well, we know how to do that, don't we? We just learned how to do that. So the first thing that we need in finding the inverse of a matrix is its determinant. So I'm going to multiply my first diagonal. 2 times 4 is 8. I'm going to subtract. Then I'm going to multiply my second diagonal. 1 times 5 is 5. Okay, so 8 minus 5 is 3, so my determinant is 3. Now I do my swap and change. So I'm going to swap the numbers in the first diagonal, so the 2, 4 becomes a 4, 2. And then I'm going to change the signs on the 5 and the 1. So that's now a -5 and a -1. And now I know that my last step is to divide each of those numbers by the determinant, which is 3. So I need to divide each number by 3 or multiply by a third. So let's go ahead and do that. So I'll have 1/3 times 4, which is 4/3. I'll have 1/3 times -5, which is -5/3. I'll have 1/3 times -1, which is -1/3. And then 1/3 times 2, which is 2/3. So it's kind of common to get fraction entries in your inverse matrix. So this is the inverse of matrix A. Now, to solve the equation, we need to multiply A inverse times B. So we need to do A inverse times B here. Now, here's the deal. This matrix here is my inverse. I'm supposed to multiply this matrix by matrix B. And that's no big deal, except that this matrix has all these fractions in it. And I mean, that's not that big of a deal. We know how to multiply with fractions, but I would suggest that when you're solving these systems, that even though this is the inverse matrix, okay, if you're asked find the inverse of this matrix, this should be your answer. But for the purposes of solving this system, I suggest that we just leave the inverse like this. with the 1/3 still having not been multiplied through. So I'm going to use this as my A inverse. It means the same thing as this, right? So from now on, when I solve these problems, I'm not even going to bother with that step. I'm just going to use this. And then I'm going to multiply that by matrix B, which is 15, 9. Now here's the advantage to this. I can multiply these matrices and not have to worry about all these fractions. And then my last step can be multiplying by 1/3. Okay, so let's do this. Let's not worry about the 1/3 yet. Let's just multiply these two matrices. And I'll remind you how matrix multiplication works. We're going to multiply the first row by this column. So 4 times 15 is 60. Then we move, and we're going to add, and then we're going to move across the row and down the column. -5 times 9 is -45. Looks like I put this bracket in a little bit too soon. Oh, no, I didn't. I'll be fine. Let's move this over here. Okay, then we're going to do the second row times this column. So -1 times 15 is -15. We move across the row and down the column. 2 times 9 is 18. So we'll add 18. So let's add those numbers. 60 minus 45 is 15. And then -15 plus 18 is 3. And now I can multiply each of those numbers by 1/3 or divide them by 3. 1/3 times 15 is 5. And 1/3 times 3 is 1. See how much easier it was to save that 1/3 till the end. Now that number that's the first in your matrix, that is your solution for x, and then y is the bottom number. So my x is 5 and my y is 1, and we've solved it. Okay, let's do another one of those. So on the next page here, we have example B. First step is to write your matrix equation. Okay, so in my matrix equation, the first matrix is the coefficient matrix. So 2, 7, 3, 4. We multiply that by our variable matrix, which is just going to have an x and a y in it. And that will equal our constant matrix, which is 14 and 8. Okay, so we need to multiply A inverse times B. Now watch how much quicker I can do this now that I've gone through and explained all the steps. So A inverse times B. Let's do our A inverse. So first of all, I need the determinant. The determinant of matrix A. Remember, this is matrix A. So I multiply the first diagonal. 2 times 4 is 8. Then I'm going to subtract. We subtract with determinants. Then I multiply the other diagonal. 7 times 3 is 21. And 8 minus 21 is -13. That's a wonderful number. Okay, so A inverse times B. Let's see. For A inverse, I do my swap and change. So the 2 and the 4 will swap. And then the 7 and the 3 become negative. And I know I'm supposed to do all of those numbers divided by that determinant. So -1/13. I'm not going to worry about multiplying this out yet. Here's my A inverse that I am now going to multiply by matrix B, which is 14 and 8. Okay, so this is my setup here. I'm not going to worry about the -1/13. I'm just going to multiply these matrices. So I have to do 4 times 14, and I can do that in my head, but I don't want to make a mistake. So 4 times 14 is 56, and then I'm going to add. Okay, I'm going to go across the row and down the column. -7 times 8 is -56. Okay, on the bottom, -3 times 14 is -42. And then I go across the row and down the column. 2 times 8 is 16. Still haven't done the 1 over -13 yet. Let's add these together. 5 plus -56 plus -56 is 0. -42 plus 16 is -26. And now let's divide both of those numbers by -13. Negative 1/13 times 0 is still 0. Negative 1/13 times negative 26 is 2. There we go, easy. X equals 0, y equals 2. So the 2 by 2 determinants we have to do by hand. The 3 by 3 determinants we are going to do on our graphing calculators. We're still going to do A inverse times B. I still need to see you write down your matrix equation. So I'm going to look at all of my constants here. I'll have a column for X and a column for Y and a column for Z. So the first row goes negative 1, negative 1, negative 1. My second row, the X term is 4, the Y term is 5. There is no Z in that equation, so I'll put a 0 in the Z column. In the final equation, there is no X in that equation, so I'll put a 0 in the X column, a 1 in the Y column, and a negative 3 in the Z column. There's my coefficient matrix. I'm going to multiply that by my variable matrix, which this time will have an X and a Y and a Z, because we have 3 variables. That will equal my constant matrix, which are just the constant numbers on the right side here. 1, negative 2, and 3. Those are just those numbers right there. Here's my matrix equation. Here's matrix A, here's matrix X, here's matrix B. We are still going to find A inverse times B. We're doing the same thing, but this time we're going to do it on our graphing calculators. Okay, so I need to enter matrix A. We know how to do that. Hit the button next to the 9, hit the 3 by 3 matrix, tab, tab, enter your 3 by 3 matrix. Here we go. Negative 1, negative 1, negative 1, 4, 5, 0, 0, 1, negative 3. I want to do the inverse of that matrix, and I have to hit the right arrow again so I get out of the exponent. We are now going to multiply that by matrix B, the 1, negative 2, 3. So I'm going to go back into that button right next to the 9, and I'm going to choose that 3 by 3 matrix, but this time I'm going to keep the number of rows at 3, but I'm going to change the number of columns to 1. So that now I have a 3 by 1 matrix. I hit 1, tab, negative 2, tab, 3, bam, there we go. And so my solution is that X is equal to negative 8, Y is equal to 6, and Z is equal to 1. Now, if you don't have a graphing calculator at home, you might have to just use a Google matrix inverse calculator, find your A inverse, and then just multiply that by matrix B. Either multiply it by hand or find a matrix multiplication calculator on the internet, and you'll do that without any trouble. When you do the 2 by 2 systems, you have to show me all your work so that I can see that you didn't do it just on a calculator, okay? Last one, here we go. Let's set up our matrix equation. First matrix just has coefficients in it. So I have a column for X and a column for Y and a column for Z. So the first equation, there's a 1X, there's no Y, so I'll put a 0. There's a 2Z. Next equation doesn't have an X, so that'll be a 0. There's 1Y and negative 1Z. Third row is negative 1X, negative 1Y, and 0 for the Z. Multiply that by my variable matrix, which will have X, Y, and Z, and set that equal to my constant matrix, which is negative 1, 5, and negative 8. Okay, so I've got matrix A, matrix B, and matrix A, matrix X, and matrix B. To solve this, I'm going to multiply A inverse times B. And I do that right on my graphing calculator. Go to my matrix. Okay, tab, tab, enter. I'm going to enter matrix A, which is 1, tab, 0, 2, 0, 1, negative 1, negative 1, negative 1, 0. Hit the right arrow, hit my exponent button, type in a negative 1, hit my right arrow so I'm not in the exponent anymore, multiply that by, hit my matrix button, choose the 3 by 3 matrix, tab, This time, change the number of columns to 1, hit Tab and Enter, and I'll type in matrix B, which is -1, 5, and -8. Hit Enter, and I get my final solution, which is that X is equal to 7, Y is equal to 1, and Z is equal to -4. Okay? So there we go. That's the end of chapter 2 and everything that deals with inverse matrices. I hope that was enjoyable for you. It sure was